All right, let's restart our CC3D workshop. This will be module 6.2, modeling cell crawling, convergent extension, force with links between cells. Okay, again, this meeting is being recorded and live streamed on YouTube. So you can go back and see, revisit the module. Because we run up a little behind on the last module, I'm going to actually finish that with an example of how to model epithelial cell compartments, and then return to the links, okay? So again, feel free to go faster and slower. Use the Zoom options. If you need help, send a message in the chat, someone will help you, okay? And make sure that you complete the pool at the end of the module, so you know what how we did and what can be improved at the end. All right, so we will be talking about links today, right now. Today in this module, but I want to just go back and finish what we have talked before about cell compartments. We did a model of the cell crawling, use compartments. I have shown how to divide the cells. What I want to show now very quickly, and I already prepared for module 6.4, is how you can also use the compartment and the cluster of cells in CC3D to model this more abstract way of to subdivide the cell into compartments. So what you want to do right now is actually make a model of a simple epithelium like you have here, and create the base simulation that will allow you to do cell constriction and tissue folding, the furrow formation in tissue. So what you want to do at the end of today is make a model of this process, where you have an epithelium here, an apical, lateral and bus compartment, ECM in the bottom, cell fluid in the top, which would be the medium, and then add links between those cell compartments and leads to tissue folding, okay? This will be done today at module 6.4 by Dr. Prion at the EPOC. But what we're going to do now, we're going to use what we learn about cell compartments and choosing contact energies, internal versus external, to make a stable epithelium that will allow us then to make this more complex model at the end of the day. Okay, so you're going to be doing this, and for this module, the code for this part is already under file 6.1.2.zip, so it should already be there for you to do. But what we're doing right now, so if you can directly download that zip file, or you can follow along with me and create the model from scratch together with me, okay? So we want to make this model. We want to have cells made of compartments, and each cell will have 3 compartments: an apical compartment, a lateral compartment, and a basal compartment, like you see here, okay? And here's going to be the planar action. So you're going to create a model template, adjust cell areas, group cells together, and adjust contact energies. So basically the same step that you had before, except for the cell division part. And let's try to create a stable epithelium like we have here. And this is going to be give us a different kind of set of choices for the contact energies. So here is the plan for this section. We're going to create a model template, adjust cell areas, okay, group cells together, and then adjust the contact energies just like we had before, except for the cell division part. You're going to follow the same rules. So this is going to be an exercise for you to get really good at choosing internal versus external contact energies, okay? And all the different ways to make sure that you, different strategies to make a model niche conditions. So what you have to do now is create the model template. You can either do this together with me, or you can already download the basic cell template from this file here, 6.1.2, okay? So, ComCell 3D, open to edit, ComCell 3D project, new ComCell 3D projects like that. Give your project a name. It can be module 6.1 tissue folding, okay? Hit continue, okay? Then when you get to the dimension of the simulation, choose 350 lattice sites in the X direction and 100 lattice sites on the Y direction, and choose the X direction to have periodic boundary conditions. So the cells are actually, that will be a way to simulate an infinite epithelium along the X direction, okay? Rectangular slab, everything like this. All right, so 350, 100, X periodic. All the instructions are stored here in the history of commands. If you need to go back, okay. Then you won't need to add the cell types. So you need the apical cell type, lateral cell type, basal cell type, and ECM. Make sure that you hit add after each one of them. And you have in your list is complete with all those 4 cell types. And we need the ECM because what the basal site sees is very different from the apical site sees. So in epithelium, in a monolayer epithelium, the apical side of the cell see a liquid usually, and the basal side of the cell usually see a ECM matrix on the bottom. So very different conditions on top and the bottom of the epithelium. So that's why you have the medium and ECM flanking the epithelium. So make sure your 4 cell types is there. Hit continue. Okay, no chemical fields. Continue. And here, when you choose the cell properties and behaviors, you want contact internal. So you already start with the table of contact internal energies in our simulation. Volume flex, center of mass, and cell neighbors. So make sure all those 5 plugins and trackers are selected in your simulation. Again, contact, external, internal, volume flex, center of mass, and cell neighbors. Once you have all of this, okay, hit continue, okay, and your simulation is done. Hit done, okay. Here are the instructions again in case you get lost. So if you don't want to do this, you can directly download the zip file, and it should be exactly at this checkpoint that you have here. All right. So now this simulation will not look like you have here, right? The idea is to actually, as an exercise, I want you to actually create an epithelium just like that, okay? So this is going to be the first task you have. In the XML, go to Uniform Initializer plugin along line 83, okay? And I want to create what will be the base of an epithelium, which basically be 4 cell rows, okay? One of the apical side here, right next to one of the apical lateral side here, another one of the basal type here, and below it, a row of cells of the ECM cell type here, okay? And you can do that using your uniform initializer, okay? You make the X to span the whole dimension of the cells from 0 to 350, and the Y, in the case for the apical side, to just span a single cell layer, like apical side, like from 49 to 56, okay? And the objective now is try to use uniform initializer by copying and paste this region code 4 times in your uniform initializer and create those 4 rows of cells, okay? So that's the thing, is the exercise for now. I'm going to give you so one way to do this, you can well, you want to, in case you want to create 4 different rows of cells, you want to copy and paste the region side, call it multiple times, 1 for the apical, 1 for the lateral, 1 for the basal, and other for the ECM. And what you see here in my screen is one way to do it, okay? And notice that for the ECM, because I want to have bigger ECM cells on the bottom, I just make the width of the ECM cell row here to be 35. And I chose the Y bounding box values to actually match one another. So here's from 0 to 35, 35 to 42, which is basically 35 plus 7, which is the width of the cells, 42 to 49, and 49 to 56. So you can either try to code this yourself, or you can just download the 56.1.2b zip checkpoint and start simulation from there. So either way, I want you to either code, save, and run simulation, or download the zip file and run simulation, and tell me what you see when you run the simulation like this. Okay, Edgar got 4 different lines of cell. That's great. In Julio simulation, everyone starts falling like dust. Okay. Tell me what you guys see. So if you run this code, yes, you see cells kind of falling, something like this. Okay. And now I can ask, okay, why you see something like this? Well, the answer is already on the slide. We need to adjust the cell areas, especially if you're using big ECM cells like I'm doing here. Okay. Not only, well, there are many things you have to still do on the simulation. You first have to make sure that your cell areas are correct, okay? And you also have to adjust the contact energies. You have to group cells together. There's a very big, to-do list here. So let's go over them one by one, okay? So if you adjust, for example, if you use the big ECM cells, like I suggest you to do here in the splash screen, you have to set this target value to be appropriate. You have to set the target value not to be 7 by 7, but it should be 35 by 35 layered sites. Okay, so that should be around, well, you do the math there, 35, 35, what should that be? Okay, and adjust that, but you still have to, after you do that, well, you just all the cell areas to be exactly what you expect from 7 by 7 cell volume. You should get something that was looking like this to something that was looking more like what you have on here on the right side, okay? But you still have to group the cells together, right? To make sure that all the cells on a same column belong to the same cluster, okay? So how you go about doing that? Does anyone have an idea how we can group the cells together? Before it was easy because when you start with just one cluster of cells, you just grab all those cells until you have the same cluster ID. But now we have multiple cells. So how can we go in the Python code and make sure that you are grouping all the cells in the same cluster? Iteration neighbors. Use their special coordinates to decide which ones to group? Yes. Center of mass in X direction, more precisely as the line say. Yes, let's do that. Okay, so let's go to the Python code. That's the one I suggest. Do a looper over a cell type. Inside, add the second loop of the other cell types. If the center of mass are equal, you group the cells together to have the same cell ID. So one way to do this, you can, for example, I'm gonna show the code here. You go, for example, over all the cells of the apical site. So let's start from the top, okay? Then inside that, you make a second loop of all the lateral cells. And as soon as the center of mass are the same in the x direction, as Elena has suggested, okay, you reassign the cell 2 to be the same as the cell 1. And then you do another loop over all the basal cells on the bottom. And again, if the center of mass match, you assign the same cluster ID. And after you make the assignment, you already know that all the other cells will not be the same, so you can just break the loop like this, okay? So that's one way to do it. I think this will be the most straightforward way to do. Maybe there are other options to do that, but that is one way to, certainly one way to code it, okay? You can try to code that yourself and see if you can actually group the cells and they start looking like this, okay? Or you can instead just download code 6.1.2c.zip and just use the code already with this algorithm setup, right? So I'll give a few seconds for people to either download the code or implement that algorithm. Please let me know when you're done. And when you're done, run the simulation and tell me if you start getting something that looks like this, okay? You should start like that. If you select different colors for the boundary between cells and the boundary between cell compartments, you should clearly see that the cells are being grouped together. So what I like to do is that when I use cell compartments, I like to not have any boundary between cells, only have boundary between cell clusters. So if you're wondering how to do that, I can open the CompCell player. So let me show here the CompCell player for you. So here are the cells, okay? So what I like to do when I use compartments, I only have the cluster borders here selected, but not the cell borders, because then it makes a continuum between the cells that are made of the same compartment. And then I usually like to have my cell, the cluster borders to be dark, okay? So you can always, if you go to the, hit this button, configuration, go to cell colors, you can select the color of the cluster border and the color of the cell border, and I like to use the cluster border to be black, okay? And that should be the default configuration in the code that I'm sharing, okay? That the cluster border is black and you have no boundaries between cells, only boundaries between cells that belong to different clusters, okay? So that's just to show this, okay? So when you run the simulation, you should see that the cells are grouped together, okay, as clusters, okay? But if you run simulation and let it go, you should see that they start to kind of move around and mix, and things are not, so in other words, you have to adjust the contact interactions or energies for the cells to stay as a columns, okay? So did everybody got to this point here? If you did, please say so in the chat. If not, please ask help, and someone will help you in the maybe in a breakout room. What's a too good target volume for ECM? Well, if your ECM is, you set by 35 times 35, then you should use 35 by 35 as a target volume. So that will be 1,235 lattice sites. So target volume for ECM, this should be a good one. Oh, you have to write the full value, right? If it's on a Python level, you can directly do that. If it's on XML, you have to write the end of the result directly. Yeah, because if you use the same target value for the cell, then everything is going to go down, right? The ACM will shrink from the niche condition. Okay, the grouping assigns same cluster T, making sure that the cells belong to the same cluster. But you still have to go and change the contact energies, right? So if you just do that, it will not be enough. It won't have meaningful meaning if the external contact energies are different from the internal contact energies. So that's what you have to do right now, the next step. So is everybody at this point here? If your target volume is still not working, okay, so the target volume should be set up at the XML level, right? And it should be 50, 50, 50 for the apical, lateral, basal, and ECM should be 1,225. So that's where you should add. Oh, it was a typo, Edgar. Reassign, so double S underscore cluster underscore ID. Okay. And it should have the self dot in front of it. Remember that all those options should be available on the Computer 3D Python level, okay? Okay, for some reason it's not working on my Twitter, on my Reddit, but it should be like this. So maybe I can just paste the code in the chat. Okay. And then make sure that everybody has it working. Oh, Sharon, if you have to, if it's volume here, you can only change here on the Python on XML level. To override that on the Python level, it should be volume flex. So that's the difference between volume and volume flex, local flex, when you select which volume plugin to use. So for everybody that was kind of a little bit behind, I need a few more seconds. I know there's a lot of code to write here. Are you all okay now?
Don't be shy about saying you need more time or asking questions about what to do.
This is not a seminar. This is a workshop, right? A teaching workshop. So we are here to help you. If your system is still collapsing, make sure that that on the XML, you're setting its the appropriate target volume to be something much bigger to reflect the size of the CM. So here, insert simulation, of course. Okay, does anyone, okay. Well, how big you set your cells to be. If you set your CM cells to be 7 by 7, then you just keep using 50. If you set your ECM cells to be 35 by 35, then use that value. Okay. Okay, how to turn off the cell boundary display? And open this in player. You go here to visualization, and here you can select to visualize the cell borders or just the cluster borders. You can turn this on and off. So if here in the initial condition, Melaine, you have your CMs to be 7, then the target volume, then you have many small ECM cell types, and this should be 50. Okay, if you have this to be 35, then this should be 1225. Got it? Okay, got it. Okay, so is everybody good? All right, so you should got here. You should all see your cells cluster. They have been properly clustered, grouped together, right? But then you're in run simulation, right? The cells start to mix, right? Because they actually have no addition preference between the cells, right? So what you have to do now, you have to adjust your contact interactions in order to prevent the mixing of the cells, and not only prevent mixing, but make sure that the apical sides stay on top, the base sides stay on the bottom, and the lateral side stay in the middle between them, okay? So we have to, in other words, revisit the contact energy between the cells, okay? And again, we have internal and external contact energies. And our objective here is now to reason through what those energies should be in order to make this to behave like that, okay? So here I want to have your participation to make a good choice of energies, okay? So the first thing you want to do, you want to make sure that all the cells that belong to the same cluster to be grouped together, right? So if you want to make sure that all the cells that belong to the same cluster are together, what values do you have to choose for those energies? Between lateral apical, basal apical, and basolateral. They should be medium, high, or low. So Lampro said low for internal to stay together. And yes, I agree with that. They have to be low, so they are attractive, okay? So they're grouped together and you're gonna stay together as a whole, okay? And of course, there are no cells that make contact with middle compartments or ECM compartments, right? So for those cases, you can all ignore those other values because they just do not exist there, okay? And there, in our case, where we have apical, lateral, and basal, we have no cells with two basals or two laterals or duplicate. So we can also ignore the same time interaction for internal energies. So we can also ignore everything that happens here at on the diagonal here. And there is a notice from Sharon, okay, that the apical basal, they should be on separate places from each one another. So maybe this value here, apical basal, should not be low, should be a little bit higher than before. And that makes sense. So we can actually make this energy here to be, okay, they're all low, but this may be a little bit higher than before, than the others, okay? So yeah, that's also a good choice. Why no value for ECM basal? Because these are internal contact energies. So the ECM is never part of the cell. It's something external to the cell. Okay, so that energy you actually go make a play a role on when you go to external contact energies like part. Okay. So next, what can also so as we talk here, okay, let's now talk about the contact of apical, lateral, and basal between different apical, lateral, and basal with other cells. Should that be higher or low? Okay, Sharon said low between same type, but higher between different type. Okay, so what Sharon is saying is that when apical and apical side are in contact, they should be high, should be low, but when you have an apical and lateral, they should be higher. Is that? But not as low as internal. So you are saying that this here should be low, but a little bit higher than those. And I agree with that because it have to be low, but not that low that the cell will start to mix, right? So yes, for external energies, you like to want the cells compartment to be side by side with the cell compartment. So you want to make sure that the apical side of one cell is next to the apical side of another cell, that the lateral is aligned to other laterals, and the basal is aligned to other basal. So you also want those energies to be low. But of course, you want to be low, but slightly higher. So there's a plus sign here than the internal ones. So they also be, they'll attach side by side, but not mix. Like this one is okay to mix a little bit. But of course, you also want to make sure that you have also the side apical and lateral between the others, okay? So this one, they should be higher, okay? Because you don't want this to touch this one, or this touch this one, or this to touch the basal apical sides to touch one another. So these other energies here, that when the interaction between compartments that belong to different cells, different clusters, should be high, okay? Does that make sense? Now, the next thing you can reason out, okay, is what should be the apical site energy of the medium and the ECM. Yeah, it should be high, but not too high. That's right, Green, because if you make it too high, then you start to separate, okay? So good point. Now let's look at the apical side. The apical side wants to be in contact with the medium, and we definitely don't want the apical side to be in contact with ECM. So how are you going to choose those two values here? Apical with medium and apical with ECM. Okay, so the way you should choose is that, okay, the apical with the medium should be low because the apical should like to be in contact with the medium. Okay, Lampard red type there. And apical with ECM should be very high. So high in both letters, because you definitely don't want the apical side to touch the ECM. Okay. And okay, what about the basal side? Can you apply the same logic to the basal side interaction with the ECM and the medium? So what should it be? So down. Okay. Okay. Please type that in the chat. Okay, Julio said something, Somia also said, and you're both correct. You want this, the basal side should like to be in contact with ECM. So you make that low contact energy, and the basal side should never contact the ECM, so you make that energy here high. So, or as Lampard said, the same thing as the base apical side, but reversed. Okay, so that's exactly this. We just do the same logic. Okay, now what about the lateral side? What you should do with the lateral side? Should lateral have energy higher with medium or with ECM? Or should be low with them? Or how you make your choice for the lateral interaction with the medium ECM? High and high. Super high or slightly high? Okay, so here you can either make it super high or slightly high. You do not want to make it low because you don't want the lateral to contact them. So you should be on the high side. Okay. I personally choose to make it high, but not as high as the repulsion, okay? But what you want here is to kind of just make initial guess, okay? So as initial guess, make this high or very high will be equally okay because it follows the logic. So when the takeaway message here is that when you build up when you use compartments, you have to make sure you have to make choices about the energies, internal and external. And the best way to make those guesses is first work through the logic. What should be higher? What should be lower, right? And then you make an initial decision that is an educated decision about what should be the hierarchy between, what should be higher, what should be lower. We are not telling already if this should be 100 times higher or 10 times higher or just double, right? We do not know that yet. We just make the qualitative choice of energies, add to your code, and then you adjust, okay? To make it, if it already looks good, your first numerical values that you choose, then great. If it does not, then you can make adjustments. But it's very important to make this initial choice of energies to be qualitative, like I'm doing here, and then you go on and put numbers as you wish. Okay? And then you adjust them for the correct behaviors, okay? So let's do this. We also have the ECM medium and ECM, okay? So for between the ECM cells, well, we model the ECM, you can think of the ECM as the same object, right? The ECM is not really made of cells, it's made of collagen, fibronectin, a lot of material. So you can treat your ECM cells in your simulation as a single material. So you can set that to 0, okay? So it's okay. And the ECM, you can have, it's harder to make a very big ECM from the niche conditions using the uniform initializer, because the uniform initializer, as it currently is, can only make a square cells, okay? In the future comp cell developments, you, instead of making a width, you can give a width, a height, and a depth to uniform initializer, and then you can make a ECM that's going to be a single line, okay? But right now that feature is not there yet, okay? So because we have made a very small squares, okay, then it's just an initialization issue. But in principle, it should be the same tissue, right? So you can just set the contact energy to be 0, okay? And then, of course, what should be the content of ECM and medium? Okay, so that's definitely something that should never be in contact, otherwise you have a wound in reptilian. So that is something that should be high, super high, okay? So you can add 1,000 here, value, all right? So when you make this choice of energies, okay, so we have already make a qualitative choice of energies. Now it's up to you to go to the code and translate that into numerical values, okay? And so I'm going to give a minute or two to actually translate that qualitative table into numerical values and make your own choices at first, okay? And if it works, share with us in the chat what values did you use. You can just copy and paste the code for the energies and paste in the code. And tell me what you get, okay? Then what I'm gonna do in the last slide, I'm gonna show the values that I choose, okay? And that's gonna give you a nice looking epithelium. But I want you to try it now to translate that qualitative table into a numerical table. Okay, Sharon asked if it's safe to comment out the ones that do not matter. In my experience, the ones for the external contact energies, they all have to be there. Otherwise, there is the code breaks, okay? For the internal ones, it's safe to comment them out, okay? If you just comment them out, they assume it to be 0 energy. Okay. The other thing you can do, you can move the order of your contact energies and place all the ones that do not matter at the end, so they are away from your field of view when you choose the values. I personally like to add space between those contact energies and group them together. One thing that I like to do is add space like this. So group all the medians together, and all the apical together, all the lateral, all the basal, and the ACM together like this. I think it's easy for me to see. And it kind of follow the rows that you have here. So it should be 5 values here, 4 values here, 3 values here, 2 values here, and 1 value here. Okay. And then I do the same thing here for those ones. Okay, group them together. So, did anyone got a good looking epithelium? It's okay. Well, it depends on how your epithelium should be looking like, right? Do you have a very fluid epithelium, or that looks actually the cells are more in the towards the mesenchymal spectrum? Remember the epithelium mesenchymal spectrum, they're more like that side of the spectrum, or they're more squarish, they're really stable epithelium that does not move. Then, yeah, your choice of energies will affect how movable your epithelium is. Thanks for sharing the screenshot. Actually, I can move here so people can see it. So that looks like a stable epithelium, right? So you see that the ACM has mixed, okay? The basal side stay at the bottom, the apical side stay at the top, the lateral side stay at the center. Okay, maybe that looks very stable. The cells are still changing shape, so that's okay. So that's a very stable epithelium, right? If you want them to be a little bit more fluid, maybe you can, one trick to do, you can just increase the temperature of the simulation and they will look a little bit more. Or you can adjust the energies, okay? Kirin has a more wave like that. Can you take a screenshot and place on the chat? It'd be nice to contrast NAMPRO's solution to your solution. See the slide again, yes. Here the solution from Pete. The cells look a little bit more fluid. You still have the contact energy between ECM, I can tell. So that looks quite different than what NAMPRO had, okay? So if you set the ECM between the cells to be, contact energy to be 0, okay, then this should look like this. But that looks also a good epithelium, very stable. I'm curious to see the epithelium from, here. Thank you. That looks very nice. So that's definitely a more dynamic epithelium from Kirin. Okay, so one epithelium here, another here, okay? So you probably chose a little bit lower values of the addition energies. So they all look more like wavy. Okay, so that looks very good. Okay, they all look good depending on exactly what you want to reproduce, right? Okay, so now this speed simulation with uh, 0 ECM, so it looks a little bit more fluid. Okay, so you see that you guys all make a different choice of the of what the numerical values here, but you all obey the same logic. And because you obey the same logic, right, you got in all of them, it's a stable epithelium, okay? So Edgar got also something that looks like the first version of Lampros, okay? And actually almost the same colors, okay? And just put here, right? Your apical side seems to be very, very stiff and get a little bit less stiff as you go down, okay? But that's also a good choice, okay? So the choice that I made, okay, so if I go to my next slide here, this diptylium that I have is a little bit wavy, something between what you Kirin and the others have. And these are the value of the energies that I chose. So I try to keep the energy levels to be similar to the whatever temperature I'm using the simulation, because that makes sure that always be more or less. So usually I use the default value, the value that should be the same, neither high nor too low, to be the same as temperature 10, and then I make everything around that, okay? So these are the values that I chose. Each one of you chose a different set of values. You can share among yourselves at the end, but basically, this is here, and and if you want to do this, you can use the code of 6.1.2D, okay? And what you're gonna do next on module 6.4 is actually add links between the cells and have those links exert forces that actually create a furrow in your tissue, but that's for module 6.4, okay? What I would like to do next in the next half hour is maybe just give a brief introduction of how those links work, okay? You can see that you have those lines here. What exactly do they mean? What can you do with that? So that's going to be the next set of exercise here, okay? So let me now really move forward to module 6.2, properly speaking, okay, and talk about the using of links to model convergent extension, the cellular forces, and cell crawling in simulations, okay? So, so I want to first look at this movie, okay, of a zebrafish embryo, and I want to describe everything that you see. So let me play again, okay? That's a zebrafish embryo. You see the cells, okay? And look at it very attentively and tell me what's going on. Okay, so there are a lot of things happening here. So first, you see the cells growing. So first, cells are moving down. So they are moving. There's a movement of the cells. Then the cells are seems to be converging in the center, right? Now they're moving towards the center. And all during this, they're all dividing. And after conversion, they start to kind of pull around, say, make a structure here, right? Then you form a kind of flank structure. And then the cells start to kind of rearrange again and make these other structures here that are called the somites. And since that there's one from first and then you have ones from the bottom, and then you see that there seems to be other things going on here. The cells are kind of growing and again moving towards the direction. So the idea here is to show that, yes, very beautiful. The cells are moving a lot, right? They are pulling each other. And this cannot, this is kind of patterns that you cannot have if only cells growing and dividing. Some of the observations may be driven by difference in adhesion energies, okay? But there are a lot of things here that, okay, the cells that must be actually adding force on top of one another, maybe pulling one another in order for this to happen, right? And this is something that happens a lot during the development of tissues, right? The cells do exert force on one another, okay? And like here in this movie, in order to make for the cell actually have to pull its neighbors, okay? To form those ball structures that you have seen, the cell also have to first differentiate into apical basal and sites, but also have to have forces that internal force that make the cells elongate internally, and also have forces between themselves to make sure that they kind of pull each other and make those apical sides of the cells to be very close together and make this kind of rosettes, okay? And you also need those kind of cells to pull one another and make very strong connections just to keep a tissue integrity in shape, like you have in the simulation of choroidal vascularization in the eye, okay? Macular degeneration. You have the cells lose the cohesion between the cells and they detach, and there's a simulation of your inner retina. The cell detachment because they lost adhesion and strong connections between them and the CM. Okay, so all those things can be done by the use of links between the cells, okay? So, and by links, I mean adding spring forces between the center of mass of neighboring cells. And may have this spring to be, to pull one cell towards another. Okay, so the plan of action for this and the next module is to talk about those links, make an overview of how links work, CC3D, give a simple exercise, and then work to some examples. First is how can you model cells move in CompuCell using links instead of using chemotaxis or using external forces. You can also make those cells move with those links and spring force between the center of mass and another cell or another point in space. And you can also use the links to model the convergent extension of tissues between cells and cell intercalation, convergent extension. So that's going to be the plan for this and the next module. So first, a word about links, okay? So links is basically adding a spring force between the center of mass of two cells in CompuCell, okay? This is done using the FPP or focal point plasticity plugin, okay? And the links is basically, okay, you calculate the distance between the center of mass of two cells, okay? Compare that to some ideal distance that the cell should have, which can be higher or lower, and then square that and add a lambda in front of it to make it higher or lower in energy. Okay, so that's basically the same formula that you had for the volume constraint, the surface constraint, the length constraint, but now we have a constraint between the distance between two cells, okay? And basically that's how it looks like. The lambda is going to be the same constraint. This small d will be the actual distance between cell 1 and cell 2. So those sigmas here will be the ID of the cells, okay? and compared to some kind of target value between what should be the ideal distance between those two cells, okay? So that's basically how it works. And when you create your simulation in the wizard, if you want your cells to have spring links between them, you have to select the focal point plasticity plugin in the cell properties and behaviors wizard panel, okay? And when you have this plugin, it's also a very good idea to also have the cell neighbors selected, so you can also change those links properties from the Python level, okay? Okay. Right. So how exactly does this works mathematically or in the code? So when you do a simulation, when you select focal point plasticity on the XML level, the CompCell 3D, well, the 3D editor is going to automatically place the code there for you. And you're going to see that the plugin called focal point plasticity is there. And then you have parameters, okay? And then it's going to tell, okay, between which cell types those links exist. So there are going to be links between cells of the same type, and there are going to also be links between cells of different types. So if your simulation only have cells of type A, you basically want to get one on these codes, going to be the parameters between links of cell type A and type A. If you have cell types A and B in your simulation, then you have 3 snippets of this code between cell A and A and B, and B and B. Okay, so you can have all those links going to be depending on which types of cell pairs you can have. So it'll be the number of types squared. Okay. So, and when you look here at this code, you see there are a lot of options. You have the lambda, activation energy, target distance, maximum distance, and the maximum number of junctions between the cells. Okay, very good question about Lampros. Actually, when you select focal point plasticity, okay, it automatically gives you two of those codes, okay? You have the parameters between cells that belong to different cluster, and you also have another duplicated code right below it, which will be called internal parameters, when we can set the links between cells when they are made of this, belong to the same cluster, okay? So everything that I'm talking here will also be duplicated. There will be a boilerplate code for the case when you're using internal compartments, okay? So you also be there, yes. And they all look exactly the same. The cell, if the two cell types are from the different cluster, then you use these parameters. If they are from the same cluster, right, then you use you'll be using the internal parameters, okay? Okay, so the lambda is basically, that you see here, is basically this, the strength of the constraint that you see here, and the target distance in units of lattice sites is going to be what should be the ideal distance between those two cells. So if they are more than that, they're going to be attracted. If they're shorter than that, there will be some kind of repulsion, okay? So that's how those two work. So they go directly from the plugin. But you also have a few others, okay? The maximum distance is set, okay, how far you can stretch, you can make apart those two cells before the link breaks. So that's going to be the breaking point of the link. So if the cell should be 7, and you keep pulling them apart to some external force. When their center of mass is 20 lattice sites away from each other, and go a little bit beyond that, the link breaks, and you don't have a link between those two cells, okay? The top part here says, okay, these parameters govern the links between cells of the same type or different types, what they are, okay? And here, this parameter here tells how many links a cell can have of that type. So you have simulation of which a bunch of cells, all of the same cells, but you set this maximum number of junctions to be 1, then the cell can make, you have 6 neighbors, right? But it can only make a link between one of its neighbors. And once you make a link with one's neighbor, it cannot have link between the others. Okay? If you make that from 1 to 3, then the cell can make up to 3 links with up to 3 neighbors between themselves, but you're gonna leave 3 other neighbors behind, okay? Assuming the hexagonal packing, of course. And if you set this to 6, then you make links with all of them, okay? And you basically can connect any cell that comes contact with, okay? So that's what that is used for. Of course, that still have this other problems here, activation energy and neighbor order, okay? So those 2 are used for the creation of links. So the links get, every time you have a lattice site flip from one cell towards another cell, and they become into contact, okay? You check if you should create a link between those 2 cells, okay? But the problem is that the creation of a link is basically adding, you're basically activating an energy term that was not there before, okay? So usually, if the 2 cells don't have a link, and now you are adding a link to them, okay, you're basically adding an energy term between those 2 cells that they didn't have not before. And this energy, so this is going to be a addition of interaction that is highly energetically costly. So from the energy point of view, your cells will never want to have a link between the cells because you're just adding energy to your simulation. So to make the creation of links to be more likely, you add an activation energy, which is negative, that's gonna decrease the whole energy of your cell once you create the link between the cells. So that activation energy that you see here is to make the creation of the links to be more likely from a cellular parts point of view, okay? And then the neighbor order basically determines how far those cells can be, so you can create a link. If you use a neighboring order of 1, the cells can have to actually touch each other in order to make the links. If you use a neighboring order of 5 or 7, as soon as they get close to one themselves, you can create a link. So that's what the neighbor order is to use for. And of course, you can have different neighbor orders depending on which types of cells are interacting. So that's why this parameter is repeated here, okay? So this is going to be the general one, and this is going to be the individual one for specific cell pairs. So in brief, that's how links work in CompCell, okay? Usually those neighbor order activation energy is something that you don't have to care about. What's really important is the target distance that you give to the cells and how strong those links are. Those are the 2 parameters that you really have to focus on, okay? These and these are the most important, okay? So if you want to get more to details, you can release the other slides, but these are the ones that we'll be dealing with. And of course, this other one is also important and going to be part of our exercise as you go forward. Okay, so the next set of exercises, I can show how you get them, but I'll just ask you to all go to the student materials folder and download 6.2.1, so you can already start exercise from there, so you don't waste too much time. Okay, so just download that file. But if you want to do it from scratch, it's CompCell3D project, new project, module 62_links. Continue. Leave all here as it is. Continue. And then you just want to add one cell type. So just add my cell. Make sure it pops up in the table. Hit continue. No chemical fields. Continue. And here you want contact, focal point plasticity, volume flex, and center of mass. So you can leave the cell neighbors disabled, or well, you turn that on. Turn it on, just to be safe. Okay, so make sure that you also hit the cell neighbors to make sure that it work, and then hit continue. Okay, conversion complete, done, and open your simulation in the player. And once you get there, run simulation and tell me what you see. Não carrega a lot. Lava cells just wiggling. Okay, so when you run simulation, I want to go to menu, visualization, and check the FPP links option there. Okay, because I want you to, because then it's going to show you the links that the cells have. So if you got there, you should see something that looks like this. Okay, if you don't see the links, go to visualization and make sure the FPP links are selected. Okay, and then you should see those links. Oh, nice. Okay, good. So you're seeing now. Yeah, it seemed that there was nothing happening, but there is something happening. Okay. So did everybody got something that looks like this? Not yet. Okay. Oh, your computer crash. Okay. If computer crash, instead of coding everything again, you can just download the file 6.2.1.zip. It should already be in the materials folder. I forgot to send those codes before, but they are out there. Okay. So let's talk about, so you see that, you can see the links, right? Because it's selected here, and you see that, so what's going on here? Okay, let's look at the code, okay? These are default settings for the FTP links. You should have, we only between my cell type, 10, -50, 7, 20, 1, and 1, okay? So you notice that the maximum number of junctions tag is set to 1. So that means that the cells can only have up to one pair of neighbor connected with a link, okay? So, and because, so all cells can have at most one, and some poor cells, okay, will have no links at all, okay? Because the coupling is random, you have this cell here and this cell here, or that cell here in the up corner that end up with no links, okay? So that may happen in your simulation, okay? So let's now try to change this parameter from 2 to 3 and higher, and tell me what you see, okay? So this is actually a parameter that you does not need to change in the code. You can go to the CC3D player itself, find the focal point plasticity plugin there, open up, and you can change that maximum junctions directly there, and again, you can see the links forming as you increase the number from 1 to 2 to 3 to 4. Okay, so that would be actually that would be the last exercise for this module. And after the break, we're gonna go to show what happens if you change other parameters of the links and do some cool examples of making the cell move with links and make the convergent extension of links. So that will be the plan for section module 6.3. But right now I want to try to change the maximum number of junctions that here from 1 to 2 to 3 and to higher orders, and see if you see the formation of the links. Can I erase the medium something links? You should not have the medium something links. There is no way to make a link with the medium. because the medium doesn't have a well-defined center of mass. What you can create a link with the cell and a specific point in space. So that's called an anchor. And that's something they're going to see in the next module, how you can anchors for the cells. Okay. What's the difference between parameters and internal parameters? Here in our simulation, we only have cells that belong to themselves with the same cluster, different cluster IDs. When you get to model cells and compartments, okay, then the links between cells of the same compartment are different between links between cells of different compartments. That's when you use the internal parameters for the links. The internal ones will not work here because you don't have cluster of cells yet. Okay, that's going to see in the next module, on the module 6.4. So whatever you do on the internal parameters will be ignored because you don't have cells with compartments. You should not get medium links. Maybe that's something that is on the newest version of CompuCell, you're maybe generating type 1 medium and type 2 cells, but something that does not work. If that option is appearing to you, then the CompuCell should be fixed, okay? So now you see a labyrinth. Okay, so what you guys should see when you increase the number of junctions is something that goes from this to this to this to this to this to this to this, right? So yeah, if you go from 1 to 2, the 2 it looks like a good way to make a labyrinth, a maze. Okay, 3 is going to be hard to get a maze that actually goes through, but this you actually can get. But basically, is what's happening is that the cells can have up to 2 links. Okay, here the cells can have up to 3 links. You may still get cells that do not make any link. So, for example, if you look at here, this is a poor cell that no one pair with it. Okay, of course, as you go to 4, then all the cells have at least 1 link. At 5, and then on this 2-dimensional simulation, when you set your maximum number of junctions of 6, then all the cells are connected to all of the neighbors. If it's just a few defects, okay? But then you make sure that your whole cluster of cells are connected, okay? So we can also change what happens when you change the target volume of the cells, or target distance between the cells, but we're gonna leave that for the module 6.3. I'm gonna stop here right now, and we're gonna do more advanced exercise with links on the next modules, okay? So I'll stop here, and I'm actually going to jump directly into the module 6.2 questionnaire. Please take a minute or two to answer how this module was, and this together with what I finish up in about cell compartments and making epithelium,